So here we want to answer the question, what's the furthest Messi can throw the football away from the Eiffel Tower? Now, what we know so far is that Messi is capable of hitting the ball with a velocity, or a speed rather, of 40 meters per second. We know that the height of the Eiffel Tower, let's call it h, is about 330 meters. And we expect the trajectory of the ball to take something like this, going like that, and ultimately hitting the ground. What we also want to figure out is this range, which is the distance, horizontal distance away from the Eiffel Tower. Right, now the variable here is going to be the angle at which the ball is hit, so this theta. If you imagine that theta is a very large value, say very steep, then the trajectory would be something as follows, and the range here is going to be very small. However, if the trajectory is very, of the angle is very shallow, then, for example, if it's thrown, let me get rid of that, if it's thrown as in here, right in the horizontal direction, then it might also land short. So this would be the new range. Again, this is not ideal. This is shorter than the maximum range that we've drawn out here. And so what really dictates the range of the ball is going to be the angle at which it's thrown. And we're assuming that since this is Messi and one of the best football players out there, the ball is going to be hit at a shooting speed of 40 meters per second. So how do we go about solving this? The best way to go about this is to invoke the equation of motion, the second equation of motion. That's what I'm going to write here. So the second equation of motion is s of t, which is the displacement, time t equals the initial velocity. So let's call that v sub 0 times the time plus half the acceleration times the t squared. Now, what do we know? In our case, well, we have the velocity to be a vector u cosine theta, u sine theta, where u is the speed at which Messi is throwing the ball, theta is the angle it makes with the horizontal, and so we can write it down in terms of its two coordinates, x and y, and that becomes u cosine theta and u sine theta. For the value of a, this becomes 0, negative g, where g is the acceleration due to gravity that is pointing in the downward direction, and it's the negative sign, and it has no x component, and it's the 0. So this simplifies to writing it only in terms of the two components, ut cosine theta, comma ut sine of theta minus g t squared by 2. So this is our vector of displacement at any time t after which the ball is thrown. So let's imagine that the time t is somewhere here. This is t, time equals t, and so the displacement vector here is going to be as follows. That is going to be s of t, and so this component here is going to be the x distance, and this component here is going to be the y distance, which is this value there. So this is the y, s of y, and this is s of x, s of x. Now it's better to write this in the coordinate system of the world, and let's imagine that that coordinate system is something which starts, say, here. So this is my positive x direction, this is my positive y direction, and this is my origin. So we can rewrite this in terms of the x and y components of this position. So the same position will have the x component as here, and this would be the y component up there. Now, it takes a bit of math, but it's easy to see that the x components are going to be the same. So x is going to be s of x, and y here, you take the sign and the magnitudes into account, is going to be h plus sy, where h is the height of the tower. Therefore, we can write that the position of the ball at time t, so these are all as well as functions of time as well as s, is going to be ut cosine theta, and y comma t equals h plus ut sine of theta minus g by 2t squared. So this is essentially giving us a parametrized form of the trajectory of the ball as it is hit. Now, it's best to eliminate the variable of time, because ultimately what we're looking for, we're trying to get the expression of the range, and range is going to be one of the components, in this case the x component here, and we want to express that without it being explicitly a function of time. So now we can re-express y as h plus u sine of theta, and time from here becomes x over u cosine theta, negative g by 2, and t squared is simply x squared over u squared cosine squared theta. So we can simplify this even more by getting rid of the u here, realizing sine over cosine is nothing but tangent of theta, and 1 over cosine squared theta is equal to 1 plus tangent squared theta. So re-expressing that, we are left with y equals h plus x tangent of theta, negative g by 2 u squared x squared 1 plus tangent squared of theta. So this is our convenient equation that is essentially the equation of the projectile of this ball, which is thrown from a height of h at some specific angle, theta, and as well as a function of the initial velocity, initial speed, some constants like gravity and the height of the tower from which it's thrown. So This is describing the projectile at all time points. What we are looking for is the projectile at a very specific time point, that is at the end. What do we know about this point is that here, the y, or the height of this point, is going to be 0 because it has hit the ground, and the x-coordinate of this point is going to be what we would define as the range of the projectile. So we can re-express this equation as for that point, and so in that case y becomes 0, x will be replaced with r, and that gives us 0 equals h plus r tangent of theta negative g by 2 u squared r squared 1 plus tangent squared of theta. We can move things a bit around, and we are left with r squared 1 plus tangent squared of theta equals h plus r tangent of theta. So this is the expression we were looking for, which relates the range of the particle, or the ball, as a function of some of the constants g and u, as well as the important constant of the height of the tower. So at this point, we effectively have a relationship between r and theta. And in theory, one could express r as some function of theta, and if we know that, then we can figure out the maximum range would be the same expression at theta max, where theta max would have been that theta, such that the derivative of r over theta at theta max would have been 0. So this is just differential calculus, and we're going to apply the same. However, writing this as an explicit relation is kind of tricky, and it's best to actually deal with this implicit relationship, where this kind of explicit relationship is not that easily derived. And we can apply the same logic of calculus, but we will work with the implicit form instead. So what do I mean by that? What I mean is we can do this thing here. We can take the derivative of the expression, the implicit expression here, and this would be g by 2 u squared, derivative of r squared 1 plus tangent squared theta equals derivative of h is going to be 0. This is a constant, plus derivative of r tangent theta. So we're going to make a few modifications here, just for the sake of convenience. So we're going to call this u squared by g becomes L, and this reduces down to 1 by 2L, and we will evaluate this derivative to get 2r dr by d theta times 1 plus tangent squared of theta, plus the second term. In this case, we'll take the derivative of the other factor. So this is going to be 0 plus 2 tangent of theta times the derivative of tangent of theta, which is going to be secant square theta, and we are going to multiply this by r squared. And on the other side, we would have dr by d theta, tangent of theta, plus secant square theta times r. Right. So it looks kind of confusing, but the interesting thing that happens here is we know that if this were evaluated at the point where we were looking at the case for the maximum range, and when the theta was theta max, then we would have this term to be 0 and this term to be 0. So in that case, we would have been able to write 1 by 2L, and this entire term goes away. You're just left with this 2 tangent squared of theta, I'm going to call it theta max, and secant square of just tangent here of theta max times r max squared, and on the other side we would have r max squared, r max, just r max, and secant squared of theta max. Okay, so what does this give us? Well, a lot of things cancel out. So first of all, the 2 goes away. We have r, and that takes away 1 power of r here. Secant square gets cancelled out as well. So we're left with a really clean equation, which goes as follows: r max equals L divided by tangent of theta max. So this is the special property of that point, theta max comma r max, at the very end here. If this were the maximum range, that the range is related to this to u and g, which is L, and theta max in this form. So is this going to help us answer the question of what the maximum range is going to be? Well, we know u, and we know h, and we know g. So we know L, but we don't really know theta max. We don't really know what the theta, or the angle at which the ball is going to be thrown, really is. So can we get rid of this theta max somehow, given that we know an expression, implicit expression between r and theta? Well, of course. We can use this expression here, and we can substitute in this our special relationship between the range and the theta for the case when the range is maximized. And so, rewriting that expression again, we get 1 over 2L, and that is r squared max, 1 plus tangent squared theta max, that is the left-hand side, and the right-hand side is going to be h plus r max tangent theta max. All right. So we want to get rid of theta, right? Theta max. And so the best thing to do is, instead of these terms here, write it in terms of R max. So we can write tangent of theta max equals L over R max. And so this would be R squared. Oh, this is going to be L squared over R max squared. And this is going to be L over R max. So let's see what that gives us. Well, this is R max squared over 2L, 1 plus L squared over R squared max equals H plus L. The R maxes, they cancel out. We can use the distributive property and expand this bracket here. We get R squared max over 2L plus, we cancel out 1 L there, we cancel out the R squared from the denominator, we get left with 2 equals H plus L. So we're getting close. And now what we can do is we can send this off to the other side, and we get this nice expression equals 2L times H plus L by 2. Expand this out, we get L to H plus L. And so R max becomes square root of L to H plus L. There you go. So that is the expression that we were looking for. This is giving us the range, the maximum range that Messi is capable of if he throws it at an angle of theta max. However, we don't really need to know what that theta max is. It's going to be L, and remember L was simply the speed squared divided by the gravity. L times 2h, which is the height of the tower, plus L, and you take a square root of that. So we have all the values. We can in fact figure out what this range is going to be and get some physical numbers. Right, so what do we know? We know that the speed the Messi is capable of is about 40 meters per second. We know gravity is about 9.81 meters per second square. We know the height of the Eiffel Tower is about 330 meters. And there, that gives us R max equals square root. L is going to be 40 meters per second squared divided by 9.81 meters per second squared. 2 times the height, which is 330 meters, plus L, again, which is U squared over G. That is 40 meters per second squared divided by 9.81 meters per second square. We can plug in the values, and this should give us a maximum range of approximately 366.40 meters. So that is the maximum range the football can travel if Messi hits it at theta max angle. And we know that there's going to be a maximum range capable because of differential calculus and the fact that we have used it to optimize it here. And so this distance here, let's just draw it out. This is going to be, R max is going to be something close to 366.4 meters. So there's quite a distance. In fact, it's as tall, in fact taller than the Eiffel Tower. So can he kick it more than the height of the tower? Well, yes, if he throws it at that unique theta where the range is maximized. So I'll stop it here, and in the next video we can look into the expression on what theta max is. Right now we have found the range without really finding the need to know it. So there you go.